So in today's tutorial, we take a look at reconstruction in the CTL, and I prepared a few settings already to shorten up the coding process for today. So all the time we need to simulate some data, I have some pre-prepared code ready already so that we can directly start with reconstructing it. Apart from that, the same procedure as every time. I set up the typical CTL settings, included the regular headers, and put up our try catch block that I mentioned last time to give us the chance to see exceptions that we might come along in our coding. And then we can directly start with the first block in the tutorial. And in the beginning, I want to talk a little bit about the interface in general for reconstruction classes. And I will do that based on the example of the FDK reconstruction algorithm that we have, and yeah, show a little bit with respect to that. And in this first block, I start with a very simple simulation setup, just having a cylinder aligned with the z-axis, 300 projections with the C-arm set up in a short scan geometry, and I create my projections just with a raycaster projector, so no effects apart from just projection included at the moment. And we can take a look at the projections if you like. They are just plain cylinder projections. Nothing happens here because, yeah, rotationally symmetric object in the isocenter looks the same in all the views. Okay, so we can then take a look how to reconstruct this thing. And first of all, we need to create a reconstructor. This is basically completely the same procedure as with projectors. And you will also see that the interfaces look very familiar, I hope, because they are basically the same as in the projector classes, just with reconstruction and not with projection. So we create our reconstructor here. And as I mentioned, I want to start with the FDK algorithm. And the implementation is using OpenCL, so that's why you find the reconstructor in the OCL namespace. And one thing that we can do as well as we can with a projector, but sometimes for reconstructors it's more useful. You can connect the reconstructor to the message handler, and then you can pass it a boolean whether or not it shall include more details on the progress. In case of the FDK, it's not so helpful to do that because you get a message every projection that is back projected, and this will be 300 messages in this case here. So I will just connect it without additional output, and this would just give me some very rough overview of what the reconstructor is currently doing. And then we can take a look into the two different general possibilities. So in case of projections, we always have the same pattern. We pass the projector a setup and a volume, and the return value of the project call or the configure and project call will be the projections that we want to simulate. In case of reconstruction, we have in principle the same possibility to do that, to get our reconstructed object returned by value. And this is the first one that we take a look into. So it's the value return version. And this is always called reconstruct, and potentially there is some aspects going on here. So yeah, let's just put some X's here. And you also have the configure and reconstruct option as well. Would start with a capital R then, but I think you get the point. So it's very similar to what we can do with the projectors, and also directly maybe at this position I mentioned that you can also call configure in advance, similar to what you can do with projectors, or you can use the combined configure and reconstruct option, which is the one I will be using throughout this tutorial all the time. Okay, so if you want to return something by value, there's one additional difference to projectors. In case of projectors, I do not need to pass the project call the information about the projections that it needs to make, because this is included in the setup. The setup contains a detector object, and the detector gives me the information about how big the projection shall be. If I want to reconstruct something, I need to pass the information to the reconstructor, how my reconstruction shall look like, how many voxels I want, and how the resolution of the voxels shall be. So I need some kind of initialization object. And in this initialization object, I also have the option, as the name suggests, to include initialization information. If I want to start with a already existing volume and just reconstruct data into that initialization object. And in this simple scenario here, I just want to create voxel volume, and I just want to have no, I don't want actually to start with a cubic volume. I want to start with something that can become quite helpful, especially if you're using a scenario like this, where you simulate data with a CTL and also want to reconstruct this. Then you can simply create a volume that has the same dimensions as the original phantom data that we used. So I can do something like this. I can call phantom dimensions and get the number of voxels in the phantom. And the same goes for the voxel size. And this helps me to create a reconstruction initialization, which has the same dimensions as my original phantom. And now I would have the chance, which is optional, to do something like filling my initialization with a certain value. I could fill it with 0.0, but this is not mandatory, because the reconstruction classes that we have would do the job for you. If it was not initialized already, then this would be done in the reconstruction class. But I have also the chance to initialize it with any arbitrary value, like if I want to initialize it with ones and then just add the reconstructed values to that. This is something I could do, but this is not required, and that's why I will not do it here. After I've specified this initialization, I can then create my reconstruction. And this is simply done by calling, configure and reconstruct. And this gets the setup, it gets the projections. So up until now, it's basically exactly the mirrored version of configure and project, with the setup and the volume, and now we have the projections here and get the volume returned. But as I mentioned, we need to additionally specify the initialization so that the reconstructor knows what kind of volume we want to reconstruct. And if we do so, we can then go on and take a look at how the reconstruction looks like. And then we can see that we get a little bit of information what the reconstruction is currently doing. And in the end, we see the reconstructed result, which basically looks like we would expect. And you can also see that it has exactly the same size as the original phantom, and that's why it's entirely filled with something looking like a cylinder, except for the cone beam artifacts that we get at the very top and the very bottom of the cylinder. And maybe one thing to mention with this approach that returns by value are maybe two things. First of all, you get the chance to make this thing constant here. This is something that you will see you cannot do with the second option that we see in a second. And the other thing that can become quite handy, and you will see that very frequently in the remainder of this tutorial, is that we could also inline this call here. If I would only be interested in taking a look at the reconstruction, I can immediately inline that here and just see the result of that being plotted. So these are basically the two major benefits when using the value return version. When there is one version, there should also be another one, otherwise it makes no sense to speak about different versions. And the other option is to have in-place reconstruction. And in that case, you also have an initialization, but now this initialization will also be used as the memory object where the end result will be added to. So there's no additional return. And in that case, I have my initialization in one block of memory, and the reconstruction will be another memory object containing the reconstruction. And in case of in place, we also need to give us some initialization, or we could just reuse this one because we don't need it anymore afterwards. So what we can then do is, actually, no, when I'm looking at my prepared things here, I want to have another one. So let's stick to that and call that in place reconstruction volume and just create another one. And now I remember why I want to have another one. And that's because I wanted also to demonstrate you that there, of course, is also the option to create any arbitrary volume. We are not limited to just using volumes with the same dimensions and resolution as the original phantom, because you can imagine if we don't have simulated data but real data, we don't have an actual phantom. So we need to specify that on our own. And one very simple way of doing it is just using the cube method of the voxel volume and then just give it some suitable numbers here, initialize with 0.0, for example. Typically, this is what you want to do. Start out with nothing and then reconstruct the data into the volume. And to do that in place, we can just use our reconstructor and then call configure and reconstruct too. So maybe we could, in the same way, give it like this syntax here. And then you would also always find the 2 here, indicating that it will reconstruct the things that need to be reconstructed into the volume that you pass to it. And otherwise, apart from that, it's exactly the same. You pass it the setup, the projections, and then the initialization, which is at the same time also the result. So one difference that this approach has, it returns a Boolean value, which indicates some information about the success of the reconstruction. So we can grab that, or we could also display it. So this will just tell us true or false whether or not this reconstruction process is considered to be successful or not by the reconstruction class. You could also grab this information in the configure and reconstruct version by passing it a Boolean in the end. So we could do the similar thing here by just passing it the address of the Boolean and then taking a look at this. So there's no limitation in one or the other approach. It's just a different way of how things are handled. And depending on the situation, one or the other approach might be more suitable. So you need to decide that based on your application, which is the better option for you. Yeah, and then we can, of course, also take a look at the result. In that case, it's the in-place reconstruction volume. And this should look pretty much the same, just that the dimensions of the reconstruction volume now are a bit different. And you can also see that we have 2 times true here, so both reconstructions are assumed to be done or carried out successfully. And in this second situation, we have specified a slightly larger volume, and that's why we have this margin all around the object itself. Okay, so this is about the 2 different options, and as I mentioned, there's also the option to first of all configure and then just call reconstruct or reconstruct too. This can be split in the very same manner as with the projectors. And then there's also something that is a bit similar to what we've seen in the last tutorial. It's the applicability. So we can check whether or not the reconstruction class itself considers its algorithm to be suitable to reconstruct data with respect to the setup and the projection information that you pass to it. And what kind of checks are included in that query, you need to read that in the documentation, because that differs from implementation to implementation, what is considered to be necessary to do a reconstruction properly or not. And you just get the chance to check that if you want. So you can do something like reconstructor is applicable to, and then you can give it a certain setup. In our case, the setup. And maybe let's just And in this case, we have short scan, and just check whether or not we are applicable to that. And to make things a bit more interesting, let's see what would happen if we wouldn't have simple short scan trajectory, but we switch to a wobble scan trajectory. So we learned that last time. We can just remove everything from our setup and then reapply preparation protocol. And in that case, I want a wobble trajectory, same source to isocentered distance, and then just repeat the applicability check. And we would assume that the implementation will tell us that it is not applicable because the FDK algorithm assumes a circular orbit around the object. And yeah, so let's verify that this is actually the case. Let me just remove the reconstructions here so we don't actually need to spend time for that. And then we can see that the output provides us applicability to short scan is actually true. And then we already get a warning, which is issued throughout the is applicable call, where the FDK reconstructor detects a non-circular orbit, tells us that there are source positions, in our case 240 of the views, that the reconstruction class assumes to be too far away from the circular orbit that it estimates from the setup that we pass to it. And then it will tell us it considers itself to be not applicable or unapplicable to the data that we want to pass to it. And this does, however, not prevent us from using it anyways. So we could just ignore this information and say, well, I don't care. I just want to perform the reconstruction. And yeah, so we can run it anyways. Problem is that there is no guarantee that the result is reasonable. So there might be some strange behavior. The results might be unphysical or something like this. So be careful if you do something in this regard, but it is possible to carry out the reconstruction anyways. Can be list. So we can just go ahead and let's do it manually. We can just do the in-place version. And let's see how the result looks like. And maybe one additional thing I want to do here. Okay, we do it in the next cycle. So we can see that this is our result, and maybe this was not the very best idea. Let me use this volume here, which is a little bit bigger because this gives us a chance to take a bit more look into the result. And I can do the thing I want to also grab whether or not this reconstruction is assumed to be correct. And because this gives us something to talk about, because this Boolean that is returned with respect to was the reconstruction successful or not is not the same as being applicable. So it is possible that a reconstruction is considered to be unapplicable, or is it inapplicable? It's inapplicable, I think, to the setup, but still the reconstruction process itself can be considered to be carried out appropriately. And this is the case here because there were no technical difficulties, no whatever memory issues or something like that. The FDK reconstructor could put the projection data in the volume, and that's why the result of this Boolean is true in the end. Although it was considered to be not really suitable for the data. And the non-suitability you can see if you take a look at the edges of our volume here, which are quite heavily distorted because we are assuming a circular orbit for FDK reconstruction, but actually have a wobble trajectory here. Okay, so that's about it for the FDK and for the generic interface of reconstruction types. And we can then head over to the second part, which is focused on iterative reconstruction. And the implementation that we have available in the CTL is implementing the algebraic reconstruction technique, or in short, typically referred to as ART. And my simulation setup that I've prepared here is a little bit more extensive. So we have a few different things that we want to take a look into. First of all, we can see that we have the same, or more or less the same phantom cylinder in the Z direction. We use only 50 views here to make things a bit more computationally inexpensive, so we can do iterative reconstructions in a reasonable time here in the tutorial. Same trajectory here. Later on we will shrink the problem size even further to make it a bit quicker. But the difference here is we use the standard pipeline. This will introduce Poisson noise to our data. And then in addition to the short scan data, we also will be taking a look into wobble trajectory data from the example above and see what the ART reconstruction of such data looks like. And then we also take a look into a low dose setting using the information that we saw in the last tutorial, using a prepare step to prepare our setup with less milliampere seconds used per view, so that we can get a bit more typical low dose situation. And yeah, so let's start with the reconstruction with the ART. So the first step again is creating the reconstructor. And in this case, it's the ART reconstructor. And we do the same thing as we did before we connected to the message handler. And in this case, we pass it also the true here to give us a bit more detail about the progress, which in case of the ART reconstructor will be the information about which iteration is currently running, which can be very useful information to estimate how long it will take for you to wait until it's finished. And then the same procedure as before, we have an initialization. And here I want first of all a cube with the same dimensions as we had before. So what I'm doing now is basically reproducing the setting that we had in the first tutorial block with the FDK, and now just taking a look how that looks like with the ART reconstruction. And yeah, that's all we need. We can then go on and straight away reconstruct everything. The initialization. And then you can see that you have the reconstruction progress, which gives you the indication of what iteration is currently running. So by default, we will speak a lot more about different stopping criteria later on, but by default, the ART runs 5 iterations. So each of these progress steps is one iteration of the ART algorithm. And yeah, once it's finished, we can take a look into the result. And if we view it from in a different slice direction, we can observe also some cone beam artifacts in the ART reconstruction here. So what about the reconstruction of the wobble scan? So note that this is the regular projections. This is the projection set that I simulated with a short scan trajectory. And then I can do the same thing to reconstruct the wobble data. And for that, just simply change up our setup, because we need to tell the reconstructor that now we are reconstructing data from a wobble setup and no longer from a regular one, and also plug in the wobble projections here. And we can reuse the same initialization because it will not change, since this is the value return version. And then hopefully we see some difference, that we get rid of some of the cone beam artifacts. But maybe and one thing that we can also will obviously also notice is that there are no more additional artifacts. When you remember what the FDK did, there were even more significant artifacts when I tried to reconstruct the wobble data, which normally should give us a better reconstruction because we should not suffer so much from cone beam artifacts with this trajectory. And if we compare these two results, maybe get a bit bigger, then we have the regular trajectory on the left, and we have the wobble scan trajectory on the right. And as you can hopefully see, the amount of cone beam artifacts that we find is substantially reduced when using the wobble trajectory here. And it's straight away reconstructible with the ART reconstruction. Okay, so that's about the trivial part of using the ART without any modification at all. And we can now speak a little bit about adjusting some settings that the ART reconstructor offers us and see how they impact the reconstruction. So the first thing I want to speak about is subsets. By default, the ART technique we implemented here uses the ordered subset scheme to accelerate the reconstruction process. And the default setting is that it uses a transition scheme. That means it starts out with a high number of subsets containing very few projections only. And with each iteration, cutting the number of subsets in half so that the number of projections that goes into one subset is increased each iteration. So in the end, you're using only a very few number of subsets with a lot of projections in them. And by doing so, it's accelerating the reconstruction process quite substantially. And in case the default settings are not suitable to the application you have, maybe you have very noisy real data and you don't want to start with very few projections in one subset, there's of course the possibility to change that, and this is what we are looking at here in this section. So the first thing we can change is the boundaries. That means how many subsets are there in the beginning of the reconstruction procedure and how many subsets there should be at the very end. And yeah, changing the boundaries of our transition scheme. This was supposed to be a white space. And for that, we can take the reconstructor, and this reconstructor object has a so-called default subset generator. This is the subset generator that is used by default if you don't provide your customized one. And this default subset generator has quite a lot of settings that you can change. And the one that we want to take a look into here is the subset bound option. So we set as subset bounds, and the subset bounds are specified by the initial number of subsets and the final number of subsets. So by default, let's just give you the information on default. These bounds are the number of views in my setup. So I start with as many subsets as I have views in my setup, meaning that I have one view per subset, and I would end up with only a single subset containing all the views in the setup if I were to execute enough iterations to reach that point. Remember that the number of subsets is cut in half each iteration, so it takes a few iterations to reach that one single subset, but this would be in theory the lower limit of the subset count. And in this example here, I want to change this to, what do I want to change it to? 10 subsets in the beginning and then bring it down to 4 at the lower limit. And if I reach the number, if I reach 4 subsets and I continue with more iterations, then it will stick with 4 subsets. It will not further reduce the amount below the number of 4. And yeah, then we can just take a look at the result. And to make things shorter for us, I will remove the reconstruction attempts here. And maybe let's, does not really actually matter, but let's switch back to the default trajectory. And I mentioned before that I want to bring down the problem size a little bit. I prepared something already here, so I replaced the detector by a very small one just to make things a bit quicker. And I also want to change the initialization to a smaller volume. And in this situation, I want to keep the in-plane resolution of 256 voxels, but I only want to reconstruct 50 slices and no, I'm not even compensating for a larger volume because I also reduced the size of the projections and of the phantom. So I'm fine with the same resolution in the Z direction. And just for the purpose of being 100% safe, I fill it with 0.0. Again, this would not be necessary, but just to make things 100% clear that I don't want to start with anything arbitrary, but with zeros. And you can see that the process is accelerated quite substantially. And what you can also see, maybe it was not the very best idea. Let me just reinstall this reconstruction without changes to the subset count, so that you trust me that I did not change anything only because I changed the problem definition. So this was the reconstruction that we had previously with the unaltered version, where we start with the number of views as the initial subset count. And this is the reconstruction where we changed it, and you can see that the result is not fully converged yet. It's still kind of blurry on the outside, on the edges. And this is because if I start with a lower number of subsets, I don't have as many updates to the volume than I would have if I started with a very high number of subsets. But there are situations where this might be required to stabilize the reconstruction process. So it's quite convenient to be able to adjust that to the precise requirements that you find yourself in with the reconstruction task. And yeah, besides just changing these transition scheme boundaries, one thing we can also do, or maybe let me just briefly show you a bit more details what's going on here. And to do so, something we can do is we can give ourselves a little bit more detailed information about the process by whitelisting the ART reconstruction. So I did not speak about that in explicitly, but you know that from previous tutorials, I'm blacklisting debug messages here. And this also applies to the ART method, and it would normally give you a lot of information about the subsets and all this kind of things, but they would be blacklisted now if I whitelist the ART. Any substring of the class name is sufficient here, by the way. Then we get a bit more information about the subsets and can see what happens actually. So what you can see here is that the subsets in the beginning start with, I don't want to count them, but that should be 10 subsets containing 5 views each. And then we cut that in half, have 5 subsets, and then the ART wants to cut that in half again, would end up with 2 because it's always rounding down. But it was not allowed to cut it down to 2 because I specified 4 as the lowest number of subsets. So we have 4 subsets here, and then we stick with these 4 subsets for another 2 or 3 iterations. And for whatever reason, I cannot scroll all the way down when I zoom in here. Strange behavior. Okay. And yeah, so another thing that we can do is we can change this pattern after how many iterations the transition will take place. Yeah. So we can change the transition period. And this is simply done by telling the default subset generator that our transition period in that case shall be 2. So that means every 2 iterations we want to cut the number of subsets in half, instead of previously where we cut it in half after each iteration. And as you can see, it's exactly what happens. Iteration 0 has 10 subsets, second iteration has 10 subsets, and then we continue with 5 subsets for 2 iterations and then reduce it down to 4. which is our lowest number, our lower bound for the subset count. Okay, so what else can we do with the subsets? We can also disable the transition scheme altogether. Or to put it in other words, we can use a fixed subset number. And this is done by calling set fixed number of subsets. And I want to demonstrate that with only one subset. So this would be just ART without any subset pattern at all. And as you probably already expect, this even makes convergence slower than we had it before. So we end up with a very unconverged result. And yeah, this would take us quite a few number of iterations to reach a fully converged result. But we speak about stopping criteria and convergence a bit later on. Okay, so there's an additional aspect going on in iterative reconstructions, and this is a so-called relaxation, which determines how much of the difference between the current estimate of the projections, so the forward projection of our current volume estimation, and its difference to the actual measured data, how much of this difference gets back projected and applied to our volume estimate in order to make it a better estimation. And this is typically something that is quite difficult to really fine-tune precisely, because making it too low, the relaxation, means you require a lot of iterations to reach fully converged results. And if you put it too high, then you end up in a diverging scenario where you will never reach a proper reconstruction result. The way the ART reconstructor and the CTL works is that it uses an estimation method inside, and this is used by default, so it has some automatic estimation. And if you're interested in what that is, it's called the power method, and you can read some details about that in the documentation. And I will not go into detail with that here. I will just show you that, the reconstructor, that you can actually call that on purpose if you want. That's not necessary because it's done automatically, but if you want to do that on purpose, you can call set relaxation by estimation and then pass this the setup you want and also the initialization. And this will set an estimation parameter and relaxation parameter to the reconstructor that is based on this power method estimation. And afterwards, you can query this parameter from the reconstructor by call to relaxation. And this will give you the information what relaxation parameter will be used based on that estimate. And we can just look what this looks like. So this will give us this estimation for the relaxation parameter, and this was the one that will be used internally when we call the reconstruction without any adaptations to the relaxation. So when there is a default mode that estimates, there's of course also a version where you can specify it manually. And this is quite straightforward. You just say set relaxation and then put in any arbitrary number. So we know that 0.02 is the one that gets estimated. So what if we use 0.001? Let's just give ourselves the reconstruction result here. Oh, no, that's not what I want, because I want to get rid of this entire subset thing altogether, because I don't want to change the subset settings. I just want to use the straight out of the box settings that we have seen previously, where we reached a fine reconstruction result. And now we do the same, but we changed the relaxation parameter manually. And what we can see is that by bringing this down to just half of the estimation, we can already see that convergence is not as good as it was before. So it's already a little bit too low. We need more iterations to reach the fully converged result. And yeah, that brings me to the two dangers that we have in manually selecting the relaxation parameter. One I already mentioned, or I mentioned both of them, but one we've seen already. If we put it too low, then we get slow convergence. And to make that even more clear, what we do now is we set our relaxation to just 10% of the estimate. So let me grab this as the estimate. Oops. And if we put it just at 10% of the estimate, reconstruct, and to make things a bit more quick, we put in the second danger at the same time. And the second one is, of course, we put it too high. And this will end up in divergence. And for this example, I want to set it to 10 times the estimate. Should be a float, I guess. And then we take a look at this result as well. And what we can see is that the first result is very blurry. It's slow convergence because we've chosen a very small relaxation parameter. And the second one, there's no meaningful result at all. It's diverged. There's no, just the iterative procedure cannot reach a meaningful result when we apply too much of the difference between the simulated and the actual projections in each iteration step. Okay, so that's all about relaxation. So we also get rid of this block here. And this brings us to the last part of aspects in the ART that I want to talk about, and this is regularization. And regularization is an additional penalty term that we can introduce to the cost function that is optimized in the iterative reconstruction process. And this is typically used to control the amount of noise that we have in the final result by making some assumptions on the smoothness of the object. And this is carried out by applying regularization after each iteration. Or in the case of the CTL, after each subset is being processed, the regularization is applied to the volume. And for that purpose, we have a few regularizers available, and we will demonstrate how that looks like here. So first of all, we want to take a look how it looks like if we don't regularize. And for that purpose, we switch over to the low dose setting that I mentioned in the very beginning. So first we look a little bit on how this low dose projections look like. And then we want to reconstruct them. And this is very straightforward. We just use our reconstructor and reconstruct. This is done with the same setup, but just with different. So basically the setup is not entirely the same because the tube component would have a different milliamp per second setting, but this is something that is absolutely unimportant for the reconstructor because it does not use this information at all. So that's why I can just use the same setup as I used previously. There's just no difference for the reconstructor if there's a change in the settings of the milliamp per seconds used for the projections. It's not considering any kind of statistical informations about the projection data. And then we can plot that result. And let's see how that looks like. So this is first of all the projection data in our reduced setting with a smaller detector to make things a bit faster. Let me try to find a windowing where you can see that we actually have a bit of noise going on. Yeah, so a bit noise in the data, and this is the reconstruction result. Let's also zoom in a little bit. Maybe we can also adjust the windowing here a little bit, and you can see that there's noise in the reconstruction result. And what we can do now is we can apply a regularizer, and this is done by setting a regularizer to the reconstructor. And as I mentioned, we have a few already prepared. Typically, you can also find most of them in the OCL namespace, which allows you to use the OpenCL version. I think all of them also exist in a CPU implementation, which does the same thing, but it's just way slower than the OpenCL implementation. And since you're using OpenCL forward and backward models for the ART anyways, there's not really any substantial purpose to do that on CPU here. Okay, so what I want to use here is the TV regularizer, which aims at minimizing total variation in the reconstruction. And this object has one parameter constructor taking a regularization strength, and details on what that exactly means can also be found in the documentation. Just to make things brief, it's some kind of amount of difference between an object with 0 total variation and the one that you have. So the difference needs to be corrected to get towards a result with 0 total variation. And this strength determines how much of that difference is applied to make a correction to the object. And something that I want to use here is a value of 0.1. And the details on how this value is scaled internally to fit the reconstruction, you can find this in the documentation of the regularizer classes. And then we repeat our reconstruction. So same thing as before, and also same thing with plotting it. And hopefully this will change how results look. And I think it's quite easy to observe that we end up with a way less noisy result here. And we can also verify that, for example, by taking a look at a contrast profile here, and I think you can see that there's a substantial difference in the amount of noise that we can find in the data here. Okay, so maybe as a comment on using regularization, of course, you need to be careful not to overdo it, especially with real data. When you put up regularization too high, then you end up with the over-smoothed image with the loss of boundaries and potentially producing an artificial look to the image. So it needs to be selected carefully. It's pretty similar to what the aspect with the relaxation is. If you put it too low, there is no effect at all with regularization. If you tune it up too high, you over smoothen the result and end up with maybe too much loss in spatial resolution to produce a meaningful result. So it requires a little bit of hand tuning sometimes to find out an appropriate regularization strength for the problem that you're facing. Okay, so this brings me to the end of my part for the ART reconstructor, and I already indicated it a little bit that there are different options when you want to stop the reconstruction. We call that stopping criteria, and what I've used here throughout all the examples is just always running 5 iterations and then stopping the reconstruction. But there are of course different options, and a few of them are implemented, and the details will be discussed a little bit now by Robert.
Okay, so let me just first of all ask into the round, should we have a 5-minute break, or is it okay to directly proceed? What do you think?
don't mind continuing, but remember to switch the monitor stuff and microphone.
Mm-hmm.
Okay, then when it's fine for all, then I would share my screen now. All right, so yeah, let's start with the stopping criteria that we have implemented here. So first of all, I want to point out that you can find an overview of all available stopping criteria in the documentation. And so this is basically a documentation of an enum, an enumeration that encodes the possibilities of several stopping criteria. And at this point, I could already stop and say, here you have it, and that's it. But I would like to give you some more insights, some more understanding what the single criteria actually mean. And for this, I would go one step back and have a short recap on how the RT that we have implemented actually work and what the structure is of the algorithm. And as you have, I think, seen a lot of times, what we are considering to reconstruct or to solve here is this X, which is interpreted as a vector of a linear system. So the X is the volume that we want to reconstruct. The A is our system matrix, or in general, it's our projector that we use. And on the right-hand side, we have our projection data that we have measured. So basically, the A is something like our setup, or it's actually the projector, and the projector uses our setup, and with the size of our problem, the system matrix A is specified. And as we all know, if we have some noise in the data, if there's noise in the vector B in our projections, we do not have any solution of the linear system at all, because there might be some contradictory information. So it would result in an inconsistent system. And instead, what we usually solve is this least square problem here. So we minimizing, or we would like to minimize the projection error. Yeah, and we know that it cannot be exactly zero, but we want to find a solution that has the smallest projection error. And one can show that this optimization problem is equivalent for searching a solution of the so-called normal equation, which is written here, which is basically something like the gradient of this objective function here, and it is set to 0. And one can show that both problems are basically equivalent. And one algorithm that solves this equation is a very simple one. It's called the Landweber iteration. And this is also what we are actually doing here. It's written down here. So we have an initial X, or a current iterate state of our vector X. And what we do is we subtract the back projected, so A transpose is our back projector, projection error AX minus B. And then we are weighting this back projected error with a certain number, which is positive and which should not succeed a certain real number, because as we have already seen by the presentation of Tim, we would not get a convergent algorithm, and we have a diversion of the solution. Okay, and what happens if we introduce our subset scheme, which is used by default that we have seen? What we do is in this language, we subdivide basically our system matrix into subsystem matrices, into blocks. And we do this we separate it in a number of subsets. And what we do is we update our vector X by just using one of these subsets already. So if we do it for all the subsets that we have number of subsets times updates for the same, let's say, amount of computations, because we only have to forward project the subset, and we only have to back project the subset in each sub-iteration. And in total, it's roughly the same computational load as forward and back projecting the whole system. It is not true, as we have seen. So maybe you already recognize it, that if we have very small subsets, then each sub-iteration also takes a little bit longer. And so, by the way, if I say sub-iteration, I really mean the update from one subset and all sub-iterations together, which means that we have processed all subsets, defines one iteration in the end. And an iteration with many subsets is usually a little bit slower than an iteration with a few number of subsets. But in the end, we are speeding up basically our algorithm approximately by the number of subsets. So if I double the numbers of subsets, I'm expecting roughly to have the double speed. And when you look closely here, then you also see this new factor R that I have introduced here, which is the ratio of the total number of views to the number of views per subset. So this omega that we have seen here is basically scaled by this factor in order to achieve the maximum convergence speed or an optimal selection of this factor here. And there are two edge cases. If we say, okay, we have only one view in a subset, which is the default start of an ART reconstruction. Then we have this also called SART type. So we are updating after each single view our system. And we expect also to have the maximum speed in this setting. And on the other hand, if we set the number of views per subset to the total number of views, then we obtain the SIRT type, which stands for simultaneous iterative reconstruction technique. And what we expect here is, of course, the slowest speed, but also on the other hand, the minimum of noise, because the noise is, as we remember, is minimized with respect to the whole system and not with respect to the subsets that we have in, for example, this case here. Okay, so, and maybe just a side note, if you do this manually selection of the relaxation that Tim have shown, then this factor relax here is defined as the product of omega and the total number of views, which means that internally this number is simply divided by the number of views per subset. Just to keep in mind, if you play around with the opportunity of manually setting this relaxation, this product is meant to be set here. And one application why you would do this is, for example, if you consider a performance critical case where you don't want to spend time to each time estimate the relaxation newly. So if the setup is well known and also the problem size, then you can pre-compute this relaxation parameter, and then you can simply set this by this setter method. Okay. So now coming to the stopping criteria. We have very simple and handy ones. The first that we have already seen is the maximum number of iterations, which is set to 5 by default. And it's appropriate to use it if you just try out a certain setting or experiment and play around with the ART reconstructor. And if you are going to do it much or even more simpler, you can also specify a maximum time. If you just want to see, when you think of, I have time for 1 minute, and you set it to 1 minute. And if you specify more criteria at the same time, it would stop at this point where the first criterion is fulfilled. So when the maximum time kicks in first and the maximum number of iterations is not reached, then it will stop after, let's say, 1 minute, for example. And maybe just have a look how this looks in real code. First of all, I have also set up some experimental setting here. I did not create, or I do not create the simple ball phantom like in Tim's case. I want to have it a little bit more complex. So I also start with a ball, but I put it into a composite volume, and then I put in a second ball with a slightly smaller radius, 35 instead of 40, but the opposite attenuation value, so a negative attenuation value, which means that in the end I should get something like a spherical shell. And additionally, I also create some disks, so 3 disks with different offsets, so that I overlay a disk phantom. And then I just also have a setup with 100 views. I have a C-arm system, and I also apply a wobble trajectory, which is, I think right now, some kind of a symbol for the CTL. And I do the simulation with the simplest projection method with the naked raycaster projector. And then I use the default settings of an FDK reconstruction and of an ART reconstruction. And let's see how this look like. So as you can see, it almost immediately starts with the ART because it takes the longest time. On the other processing steps were very quickly finished. So this is how the wobble trajectory looks like. And this is how the projection data would look like. So we see this spherical shell in the center, and due to the wobble, we see the disks from different perspectives. And what we would expect from such a trajectory, again, is that the FDK is not able to accurately reconstruct this wobble trajectory, which you can see here. And if we use the same data in an ART reconstructor, we see that it's quite accurate reconstruct in this case. All right, so let's play around with these stopping criteria and comment the FDK out. For the sake of this example, I would set the number of subsets to a fixed number to keep it in this example as simple as possible. And for this, I can call the default subset generator, which is enabled by default, and set a fixed number of subsets. Take 20 in this case. And what I expect now is, again, that the convergence the convergence is not as fast as we have in the default case, because in the default case we start with the highest number of subsets, and now we start with only 20, which means if we have 100 projections, it means that we have 5 views per subset. And also in the default case, it will perform the same number of iterations, which means 5. And maybe you can appreciate it, but it's a little bit more blurry than in the version before. And now what we would like to have is, let's say we have the case that we have a certain amount of time, and we just would like to cancel the ART iteration after that time. We could think that we can write down, okay, maybe let's just say set stopping criteria, or let's start with this. Let's say we say set max time, and then we specify, let's say 12 seconds. And by default, if we use such a method without any further argument, it is set to true. But now what is done here, the max time criterion is additionally set to the criterion that we had before. And before we had the default case, which means it stops after 5 iterations. So it will not go to 12 seconds, because first the maximum number of iteration criterion will kick in, as we can see here. Before it took only 4 seconds. So this will not work. So there are now different possibilities how to disable the maximum number of iteration criterion. And one would be to say set stopping criteria. And now we are able to specify this enumeration value that where I have shown this table, and it's encapsulated in the ARTReconstructor class. And there is one criterion which is called no stopping criterion. So with this approach, we disable all stopping criteria. And if we would outcomment this line, for example, the algorithm will never terminate. Now it will go forever, but that's not what we want. We want to stop after 12 seconds. Let's see if this works. And in fact, it works. And what we can also see is that the image quality is again much higher. So we have a quite sharp reconstruction available, even if we still have this setting with the 20 subsets. Yeah. So another possibility, by the way, would be to disable only the criterion on the maximum number of iterations. So what we could have also done is that stopping criterion enabled. And here we could specify ARTReconstructor maximum number of iterations. And we could say, okay, we don't want to enable it, we want to disable it. So enabled needs to be set to false. So just in case we know, okay, we just want to disable this specific criterion, this is also possible. So there are many ways with this interface. If you have a look into the documentation, you will see. Okay. So, and then maybe going back to the presentation, there are other possibilities which are also more intended to playing around with the ART reconstructor. There's, for example, this criterion volume domain change or projection error change, which just measured how large the updates are. Yeah. So in one case in the volume domain and in one case in the projection domain. And if there is not really a change anymore, or it's below a certain threshold, then the iteration will stop. There is a disadvantage of these techniques that it depends on the relaxation parameter, as you could imagine, because if you choose a very low relaxation parameter, then we are much faster below this threshold, because a low relaxation parameter change not so much on our solution. And it also depends on the subset size. If we have many subsets, then we have a lot of change within one iteration. And so there's also an additional dependent on this. And the thing is that all stopping criteria are only evaluated after a full iteration. Yeah? So after all sub-iterations are processed, then it will check for any kind of the available stopping criteria. So what is more sophisticated, for example, is if you already know that you have a certain noise level in your data, then you could use this information and say, okay, I know that typically I have, for example, a noise level of 5% in the projection data. Then I set my threshold to, let's say, 6%. And when it's below it, then I know it cannot go much better. Yeah. If you are lucky and know this information, you can use it in this case. So here we would expect to have actually zero projection error, which is also not true, because we still have, of course, numerical errors, but we don't have any additional Poisson noise, for example, in the data. And if we, for example, set additionally the criterion that in relative projection error, and let's set it to 2%, then let's see which of both criteria kicks in first. By the way, if you whitelist the debug messages of the ART, then you see this useful information after each iteration. It evaluates the stopping criteria, and you see how far you are away from your thresholds. And in the end, you see, okay, the ART is terminated due to the relative projection error, and not because of the time. The time was 11 seconds, and the threshold of 2% has been undershot. Okay, so but what if you don't know the noise in your data, which is usually the case, then we offer also a general criterion, which is, I think, the best suited for quantitative analysis. And this checks how well the normal equation that we have seen is satisfied. Yeah? So here you can see the norm of the normal equation, and to have a reasonable dimension of the tolerance, we normalize it by the back projection of the data. And you also have to keep in mind that if you are using ordered subset, that this criterion only approximate this inequality here. Yeah, this is for performance reasons, because we cannot really compute. Or we could of course compute this norm here, but for performance reasons, it uses the information of the volume differences. It's quite similar to this one, and computes indirectly this quantity here. So so you should not expect to have completely accurate number for the normal equation ratio here. But if you have only one subset, so no ordered subset scheme, then this is perfectly fulfilled here. And I think for the most cases, if you have figured out what is a reasonable tolerance, then you are able to compare different settings of your experiment. And let's also try this. What we can also do here is to disable the previously set criteria. We can just say set it, but do not enable it with this additional false flag. So now we should have set no criterion at all. And then we can say, well, let's use criteria. Normal equation satisfied. So if we do it in this way, then we would enable this criterion, but we have not specified the tolerance. And what would happen is that the default tolerance would be used. We can also look this up if we have a look in this header class here. There you can see what are the typical default values that we have specified here. I would not trust these values, so there might be some adaptations required for your specific situation. But let's just, for the sake of this example, use the default value and see what happens. Yeah, it's also, I think, the same number of iterations in this case, but now it stops because of the normal equation criterion, which is printed here. All right, yeah. So this would be it from my part. So if you have any questions regarding it, please ask. If not, then I think we can I can hand back to Tim, who has prepared another small part of doing some fancy stuff with the ART, right?
Yeah. So as always, if you have any questions, you can also pop them up immediately if you like. And also in the end, we have our typical question session. But yeah, if there are no questions currently, then we can just continue with the last part. It will not be as long as the previous ones, and it's just about some kind of fancy stuff that you can do with the ART. Was just playing around some settings that we can do, and I think I found some interesting things to tell you. And the core idea behind it is that we want to take a look what we can do when we have spectral information, so when we have polychromatic radiation that we use to simulate, or in real data as well, and how we can do something in that regard to figure out how we can improve our reconstruction. So I set up the simulation setup here with the cylinder. Again, I'm the cylinder man, so you know that my simulations are always a little bit more simplistic, but to keep things really straightforward, I used just the cylinder here, and I created as out of soft tissue material. And I simulated with some kind of settings here in short scan trajectory, and I tuned down the tube voltage to 70 kV and used a rather high amount of dose per view. For the sake of demonstration, this is something that is well suited for the case here, as you will see in a few moments. So the first thing I want to do is I want to just reconstruct this thing straight away with the FDK. And for that, I just create my FDK, just like
I think you need
previously.
to share the screen.
Ah, that's actually a very good idea to do that. Okay, now we're back. So I was showing some things here, but I also talked about them, so we don't need to go through them again, I think. Yeah, thanks for the comment. Yeah, we create our FDK reconstructor, and then we just create the reconstruction here. And this is just FDK configure and reconstruct, setup, projections, and I've not specified my initialization yet. Why don't I have? Because I actually want to put it on top here, and I forgot. So we just use some volume here, and it's basically the same that I used before, I think, where I only have 50 slices and put 1 millimeter voxel size. Okay, just like that. And I want to, again, for this, just to be 100% sure, fill it with zeros. And yeah, then we can take a look at how that looks like. FDK. And yeah, just start with that, because I want to mention one additional aspect with respect to the FDK that I have not mentioned previously. And why is there, damn it, forgot to switch to executing, oops, the other way around, executing this method here. No, that's also wrong. Recompile first. And it is the result of the FDK straight away, as we can see here. And one thing that I want to add to the FDK reconstruction possibilities is that you also have the chance to apply an apodization filter to it to make it a little bit more smooth. And the way you can do that is you can just tell the FDK to use a certain projection filter, which is applied to the projections. And to use apodization, you can use the apodization filter class. And this offers a bit of variety between different filters. You can read that in the documentation. I will just use a cosine filter here, and you can then define a certain frequency scaling that will be used as a cutoff for the frequencies that will be used in the back projection procedure to make the things a little bit more smooth and reduce the amount of noise. A little bit similar to what you would get when you use regularization with an iterative reconstruction. And you can read the details in the documentation about what that exactly means in the context. And this was not helpful at all because I just set the projection filter and did not reconstruct again. So that just to compare both results, we have one reconstruction without apodization and one with it enabled. And you can see the comparison here that you have one without and one with apodization enabled, and you can see that you reduce the amount of noise, but at the cost of a little bit of loss in spatial resolution, as you would expect if you just cut off some high frequencies from the information that you use. Okay, so let's get rid of this for the moment and go on and reconstruct the same thing. Construct with the ART. And for that, we create an ART and just do the reconstruction straight away. I just want to connect the ART so we get information about the progress, and then we just do some reconstruction. And there's no bracket for whatever reasons. Okay, so let's just take a look at this comparison. And as you can see, there is quite a bit of advantage already with the iterative reconstruction here. But the thing I want to point out is when we take a look at the contrast profile, and we copy that line, add it here, and we can see that we have typical cupping artifact, which is due to the fact that we use polychromatic simulations here in this setting, and we just simply reconstruct without any information about the polychromatic nature of the radiation, which introduces the beam hardening artifact that in this simple cylinder phantom just expresses itself through this cupping artifact. And there are options to get rid of it by pre-processing projection data, for example, using some calibration tables and so on. But one interesting thing that you can do is just using an ART method and substituting the forward projector by a spectral forward projector, which considers the spectral nature of the radiation. And the interesting thing is that in the CTL, the ART reconstructor also has implemented a method to do that straight away. And this is activated immediately if you pass it a spectral volume instead of just a regular one. So this init here is just a plain voxel volume without any material information. But as soon as you enrich this volume with spectral information, so you give it a material, then the ART tries to use a spectral forward projector and just simulate the projections with respect to that material, and then the estimation should get better because you consider the aspect of the spectral composition of the radiation in the reconstruction. So that means the only thing that we need to do is we need to generate a spectral volume. So we want to reconstruct using a polychromatic forward model. And for that purpose, we create a initialization for a spectral case. And this is just a spectral volume data object. And what I want to have is I want to use the same dimension information as I have with my regular voxel volume. I just want to enrich that with an attenuation model from my database. And to make things not 100% trivial, I will not reuse the same material. Maybe I do not know that this is actually soft tissue that I have in my object. So my most trivial assumption would probably be that it is water that I'm reconstructing. So I create my initialization with water as the material information. And if I just use this thing here and repeat the reconstruction, but not with a normal initialization, but with a spectral initialization, this will immediately detect this and run the reconstruction using a polychromatic forward model. And you can see that in the information. You can see, first of all, we start with plain volume iterative reconstruction, and the second attempt is reconstructing it with a spectral volume. And maybe you can already see that it takes a bit longer because creating the polychromatic forward projections is a bit more computationally expensive, but hopefully we can already see that we achieved the goal that we would like to. So we can again compare the different profiles here. So this was the ART with regular monochromatic forward model, and this is now the ART with the polychromatic forward model. And as you can see, there's basically no cupping artifact left, maybe some little bit of it due to the fact that I'm reconstructing water and I actually had soft tissue, which is not entirely the same as water. But with this simple adjustment that we use a polychromatic forward model, we can get rid of the beam hardening artifacts altogether here. This, however, will not be as simple in real case scenarios, which we will talk about in the next tutorial, because in real scenarios, you first of all need to know the precise details about the spectrum that you're using. This is very simple here because I'm reusing the same setup, which has the same X-ray tube component. So it's using exactly the same spectrum for the reconstruction forward model as it did for the simulation forward model, but we come to that aspect in the next tutorial a bit more in detail. The final thing that I want to show here, or it's not really the final thing, but it brings us to the final thing, is what happens if I want to just initialize my ART with the FDK reconstruction that we have carried out previously. And then perform just a single iteration of the spectral setting. And for that, it's very simple what we need to do. We just go on and say, okay, I want to override my spectral initialization. We just copy and paste this, but instead of using the plain initialization filled with zeros, we will just use the reconstruction of the FDK. So this starts out with FDK data, uses this as initialization, assumes that the result is water, and just performs then one iteration of the ART. And for that, we already know how to do that. We set maximum number of iterations to 1, and then just simply repeat the reconstruction process. And unfortunately, we need to wait a little bit, but that builds up the tension. Does that really work? And if you should be asking yourselves what might be the reasoning behind it, it's just that we could save time in doing so, because we just need to perform one single iteration and not full set of 5 iterations, and hopefully achieve more or less the same effect. So we must be sure not to confuse things. So we have, let's do it this way. This is the FDK result here. This is the monochromatic ART. This is the full polychromatic ART, and this is the FDK initialized ART with just a single iteration of the polychromatic spectral update. And maybe you can see a little bit that the edges are not as sharp probably as they are here. Maybe when we zoom in a little bit, we can see that a bit better. So maybe one iteration is not entirely enough, but it demonstrates the power of this approach, that you can get to a corrected, polychromatically corrected result just with very few iterations of the ART scheme when you initialize already with a good estimate coming from the FDK. Okay, and this now really brings me to the final point I wanted to show you, and this is when you might ask yourselves, well, we start out with the FDK and then perform one iteration of ART. Why don't we do an iterative FDK altogether? So just doing the back projection step with an FDK algorithm. And the interesting thing is we can just simply do that with the CTL. So we can just create an iterative FDK. And to do so, we create a new reconstructor. We could reuse the old one, but just to make things a bit more clear here, I want to make a new one, and I just want to out-comment everything here, I think. Probably yes. Let's see. Otherwise we adjust it, but we don't need all of these. And we create a new ART reconstructor. And the thing that we change now is we set the back projector that the FDK shall use to the FDK algorithm. And in order to make that really a proper routine, we need to make a few more adjustments. And what we need to do, in fact, is we need to go down to a fixed subset number of one subset. And the reasoning for that is that that the FDK reconstructor does not account for random permutations of views coming in, because it needs to compute redundancy weights, and the computation of these assumes that there's a consecutive order of the subsets of the views in the data that it gets. So we need to bring that down to one subset, and we also need to change something we have not discussed yet. We need to change the order of the within the subset. So by default, within one subset, all the views will be selected randomly, and this will also confuse the FDK with respect to its redundancy weights. So we change the order within the subsets to adjacent, and this will end up with just the full set of projections in their natural order, which is also the ordering that we pass projections to a straight away FDK reconstruction. There's also no subsets, no view permutation, and so on. So this is also the same thing that we now need to do in iterative FDK. And then we create our spectral initialization. Once again, could copy that, but let's just rewrite it. And okay, I need my initialization. Didn't delete it yet, so fine. Attenuation model. The same as before, we use water information here, so I could have copy pasted that. Well, and then we compare, first of all, a straightforward approach where we just take a look at how does our iterative FDK reconstruction look like. No, configure and reconstruct. And this init spectra. No, just the plain old. I wanted to start with the straight away reconstruction. So this would use the monochromatic forward model and then the FDK reconstruction to back project the error because we changed the back projector. And for comparison, we also do the same thing, but with a spectral initialization. And this once again would use the polychromatic forward model and in combination with the FDK reconstruction as the back projector. And as you can see, there's the result of the regular FDK reconstruction without any adaptation. So it uses the monochromatic forward model, and as expected, yeah, there is nothing beneficial really in this regard because we just repeat the FDK procedure for a multitude of iterations. But in case that we want to use the polychromatic forward model, we could do that now. There's no chance to do that for the regular FDK. There is no forward projection involved. And we can see that we at least compensated for some cupping, but still have some noise effects going on in the FDK. So that brings us to the final thing that we can do. We can combine this also with regularization. And for that, we already know how to do it. We just set a regularizer. And again, I want to use TV minimization. And in this situation, since we have only one subset, we need to have a much higher strength for regularization. This is something we did not mention yet, but different from the relaxation, the strength of the regularization cannot as easily be just adapted by the number of subsets because the reconstructor does not have the guarantee that the regularizer that you are using actually offers something that is called strength. So there is no chance that there is dynamic adaptation of the strength of regularization. So this particular aspect is up to you to determine a meaningful strength of regularization when you set in the regularizer. So in this case, since I know that I will be using just a single subset, I can do a very strong regularization because the regularization will be applied way less often than when I have a lot of subsets. Okay, and yeah, then we just can copy and paste this thing here. no changes required. So we get 4 reconstructions and hopefully see some differences. And also this brings me to another idea that I have not scheduled, but maybe we can play with that final idea for a second when we've investigated these results. So let me order them similarly to before, like this probably. Find out some contrast line here. Copy that, paste, 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 and give us the contrast profiles. And then just quickly go over the results. So we have the plain FDK the plain iterative FDK reconstruction. We have the polychromatic iterative FDK. Then we have the regularized monochromatic iterative FDK here. And then we have the regularized polychromatic FDK on the bottom right, which provides us with a quite reasonable result. And probably you could appreciate that this procedure went on way more quickly than we've waited some time for the ART, and we could even bring that down way further because there's probably no need to do so many iterations of that procedure because we have a very rapid progress due to the FDK in the back projection step. And it's also a funny thing to play around with, allowing you to use regularization in combination with FDK style reconstruction techniques, also allowing you to use in a very simple way a polychromatic forward model in the same construct. I think it's quite a funny thing to do. And the final thing that just came to my mind is we could also try to play around a little bit with using the apodization in the FDK back projector here. And for that purpose, we would probably do something like that we first of all create our FDK and maybe we make it a bit cleaner for this purpose here and make an FDK reconstructor here, and then set the projection filter to an apodization filter. And I've not tested that, if that really provides nice results, so it's just an experiment here. I don't know, maybe we don't put it that strong as previously, maybe put it to let's say 0.75 maybe, and then where's autocorrect when you need it, and then we just go on and set back projector once again and use this apodized FDK now, and then do that. And maybe we can spare these because we know how these look like, but to compare, well no, actually not. Stop, because before I'm doing this I want to get rid of the regularization, which you can, by the way, either you disable it like I'm doing now by doing just a call to set regularization enabled false, then it's disabled again, or you could pass it the identity regularizer, which is also available in the CTL, which is the thing that is also installed by default, which is just doing nothing at all. But this is the simpler version, just disabling it like this. And of course, this would open up the third possibility of combining both regularization on the volume domain and some kind of regularization by apodization in the back projection step. Okay, so let's see. It's even interesting for me because I have no idea how good this works. So this was monochromatic regularized, polychromatic regularized, monochromatic apodized, and polychromatic apodized. Well, yeah, you can decide for yourselves. I think it seems to still produce some how is it called in English? It overshoots at the edges in this situation. Maybe we could lower the apodization frequency and play around with that, but yeah, I leave that open to you to experiment with that when I uploaded the tutorial code or just when you re-implement it on your own. I think it's quite an interesting idea to just combine different techniques and see what this gets you, where this gets you. Okay, so now that's really all I wanted to show. This is something new with apodization in FDK. And yeah, I'm open for your questions if there are any.
What you also could try out, for example, is set the number of iterations to 2, for example, right? So now you're doing 5 iterations.
Yeah, we could. I think I postpone that for when I end the recording session and to leave the curiosity up to the viewer to re-implement or play around with the settings, and we can have a look after this session. Yeah. It should definitely be enough for the version where we don't have the polychromatic setting and where we don't want to regularize. Regularization we could compensate with a higher strength probably, but not entirely sure if it will be already sufficient to get rid of the beam hardening. But yeah, interesting to investigate. Okay, any further questions, comments? Something in the chat. Okay, no. Good, yeah, if that's not the case, then I think we can finish this tutorial.